Now we'll talk about the operational properties of the Laplace transform, and basically these are just time-saving tools because evaluating a Laplace transform such as this is quite formidable. So let me introduce the first property, which is called the translation property, and this is given as follows, where we have, suppose we have the Laplace transform of f of t equal f of s, and that we have a constant a, which is any real number. So when we take the Laplace transform, where we have a f of t multiplied by this exponential e to the at, the resulting Laplace transform is simply f s minus a, and the proof of this simply applies in terms of definition. So here we have the Laplace transform of e to the at ft, and we're applying its integral definition shown here, where we substituted e to the at f of t into our definition. We're integrating from 0 to infinity, and we see we notice here we have a common base, so we can combine them in our exponents. So that just f of t equals e to the minus s minus a t dt. But we note here that this is just our definition of a Laplace transform, where we replace s with s minus a. And that's our first property, operational property of the Laplace transform. Will help save time in finding the Laplace transform of various functions. And we'll illustrate now with some examples. Now we're going to illustrate the translation property with these two examples shown here. Here we have the Laplace transform of e to the 5t times t cubed. First of all, we have to note that we need to find the Laplace transform of t cubed. Clean this up a little bit. Laplace transform of t cubed. Evaluated, after we do that, s equal s minus a, but a in this case is 5. We note that the Laplace transform of t cubed is 3 factorial over s to the 4th, and wherever there's a s, we're going to replace it with s minus 5. In this case, this would just be 6 over s minus 5 raised to the 4th power. So that's our Laplace transform for this function. Now we're going to do this second example illustrating the translation property, where we're given the Laplace transform e to the minus 2t cosine of 4t, and we're asked to find this Laplace transform. So here, the first thing we need to do is find the Laplace transform of cosine of 4t. After we find that expression, wherever there's a s, we're going to replace it by s equal to s minus a, and minus a turns out to be minus 2. So minus minus becomes a plus 2. We note that the Laplace transform of cosine 4t is simply s all over s squared plus 4 squared. We're going to evaluate this where s is replaced with s plus 2. In this case, the numerator gives us s plus 2, and the denominator gives us a s plus 2 squared plus 4 squared. So that's our Laplace transform for this expression here.